Okay, all right, students, we're starting our Unit 2 reviews. This is Unit 2, Part 1, and it covers 2.01, 2.02, 2.04, and 2.06. And you should be able to complete the corresponding quizzes after watching this. All right, so first of all, I want to go to our 2.01. 2.01 was a lot of reviewing material, in particular the converses. Okay, so we've already seen this before, so I'm not going to focus too much on that. It was a review of that. Equivalent fractions, you should already know how to solve these as well. This would be like if I had 2/4 and 1/2. These are congruent or equal because they reduce to the same thing. Okay, so those are equivalent fractions. So I'm going to focus mostly on the midpoint formula here. And the reason I'm doing that is because this is probably the most new to you. So a midpoint is a point that divides a line segment into two congruent parts. So if I have a straight line, the midpoint would be what cuts it in half. So if this was A, B, we would say that middle would be the middle of those two, and it would be point C. Okay, and so what you're doing is you're finding that point C when you use this formula right here. Okay, and what this formula says is it says that I can take the x's basically, okay, and subtract them, or I'm sorry, add them. Take the x's and add them and then divide by 2, and take the y's and add them and then divide by 2. The thing that you need to remember with the 1s and the 2s there, where you see x1 and x2, is that you always start with the same point. So if we're going to use the first point with my x1 first, then we have to use the y1, so the first point with my y as well. All right, continuing on here. So an example of the midpoint formula. I put that up there again for you, but basically right here is what we're trying to find. It says segment RT has endpoints -3, 4 and 5, -2. What is its midpoint? And so I'm simply going to first name these as x1 and y1 because I want to know what I need to plug into that formula. And then x2 and y2. And as I do this, I'm just going to go ahead and show you the work down here. So I'm going to plug into this formula. I'm going to start with my x1, and I'm going to do -3 plus my x2, which is 5. And then that whole thing is divided by 2. I'm going to do the same thing for my y's. So I have 4, because I started with the first point, plus a -2, and the whole thing divided by 2. Okay, so now you can see that this is -3 plus 5. Well, -3 plus 5 is like saying you have $5, you owe your mom 3, so you have 2 positive left. So it's 2/2 now, which reduces to 1. Oh, excuse me. And then 4 plus a -2 is really like saying subtraction. So we subtract 4 and 2, and we get 2/2, and we get 1 again. Now, it won't always turn out that you get the 0.11, okay? It just happens to be the middle of the 2 points that we started out with. And that, my friends, is our answer. Okay. So hopefully that was enough for midpoint. Basically just add the values and then divide by 2. So let's go on to talk about 2.02. And this was all about scale factors and dilation, and about pre-images and the images after you've dilated it. And so I want to go ahead and first define what dilation is. So a dilation is a transformation that changes the size but not the shape of the figure. So it's not changing the shape of the figure, meaning it's still similar, the figure's still the same shape, but it's changing how big or small it is, okay? A dilation is not a rigid transformation, which preserves both size and shape. So rigid meaning that it's really strict, you have to change the size and the shape. All right, center of dilation right here is the point where the line's connecting each point on the preimage with its corresponding point on the image. So center of dilation, you'll hear a lot, it's centered about the origin, or with center of dilation at 2, 3, or something like that. So that's where the points are kind of like equal distance from each other. You can kind of think of it's the point where you focus dilating it. Okay. Then we have the word scale factor. A scale factor is a dilation with a ratio of the length of the side on the image to the length of its corresponding preimage. So what we see here, this little ratio, okay, or fraction, we now call them, would be our scale factor. So you take the image, so what it is now, and you put that over the preimage, what it started out being. I like to also look at it as the actual and model, okay, that sometimes helps. So more or less, this is just us writing fractions, okay, which are really ratios. And they're two in the same thing. All right, a few more things. Positive and negative scale factors. So I put a few things up here just to remind you or show you that a positive scale factor, so this is a positive 2, is when it's going in the same direction. See how this C is our center of dilation? And they're both going to the right of C. And you can also see that A corresponds with R, okay? And B corresponds with T. All right, but if we look at a negative scale factor here, you can see if this is our center of dilation, they're on opposite sides of the center of dilation. One is on the left and one is on the right. Another thing you can see is that, remember how A corresponded with R in the positive? Well, look, A and R are now opposite of each other, okay? And so what's happened is it's kind of been flipped, and it's on the opposite side. So that's going to help you to determine whether the scale factor is positive or negative. And the very last thing here, I know there's lots of information, is this idea of expansion and contraction. So these are another word for making it bigger or smaller. So an expansion, okay, is dilating it and making it bigger. So an expansion is going to be greater than 1. So when you have this scale factor right here where it says 2, that's actually an expansion. It's getting bigger. Now I want you to understand something else here. It says absolute value. So absolute value meaning that it doesn't matter if it's negative or positive. Okay, so absolute value will always make the number positive. And so up here on these positive and negative ones that we saw here, these are actually both expansions, and you can see that. You can see that from red to blue, we're getting bigger. And we're still getting bigger from red to blue, no matter if they're positive or negative, okay? So if this number, absolute value, when you take the absolute value, or when you ignore the negative signs, if it's greater than 1, then it's an expansion. If it's less than 1, meaning it's a fraction, or sometimes you might see it as a decimal, but it has to be between 0 and 1, because we don't have negative distances or negative things can't be made bigger or smaller by using negatives. A contraction is making it smaller. So that is when we see like a scale factor of 1/2 or negative 1/2. Because really negative 1/2 just means that it's going the other direction from the center of dilation. But it's still a contraction. It's still making it smaller. All right. Let's look at some examples. Okay, so use the links to form this ratio. So we're going to form the scale factor. We're going to write the scale factor, okay, for this image down here. Now, first of all, a couple of things to note. It says the pre-image is BCDE, and the dilated image is this. So a lot of times when you see those little tick marks there, that means that the operation has been performed on it, okay? It's something's happened to it. It's the new image. Okay, so when I look at this, first of all, I want to just take any length, okay? So up here it says the image length and the pre-image length. It doesn't matter, guys, which side you take, okay? I'm just going to use this BE. And if I use that BE, then I'm also going to use this BE, okay? So the important thing is that you're using the same side length, okay? Now, we want the pre-image on the bottom, so that's what it started out being, which is this one, okay? Not the dotted one, but this one. And so I'm just going to count how many spaces it is. So I see 1, 2, 3 spaces. So that goes on the bottom, okay? And then on the top, I put the image after it's been dilated, okay? And so it's kind of hard to see because you have all these tick marks, but there's 1, 2, 3, 4, 5, 6, okay? So that side length is 6. Now, we can know that we did this right if we get out the right scale factor. So before I go any further, I want to bring to your attention, first of all, I can see, and hopefully you can see as well, that this is going to be an expansion. Going from this one to this bigger one, we're getting bigger. So my scale factor has to be a number greater than 1, okay? So if I do 6 divided by 3, or I reduce that, I really get 2 over 1, which is the same thing as 2, right? And so I know that this looks right, because I'm getting a number greater than 1. I'm getting 2. Okay, something else you need to know. Is this positive or negative? Well, if I look at this picture over here, okay, these seem to be going in the same direction. And the other thing I can verify is this. See how this one in this corner is B, and it lines up with the B image here? Okay, and then it goes E to the left, or to the right, I'm sorry, and E image to the right, and then D is up, okay, and then over. So it's going in the same direction, therefore it's a positive. Now, if it was on this side, down here, okay, somewhere like this, and then it was switched and it was like B, E, D, and C, then we would know that this is going to be a negative scale factor. So we would put a -2 over here because it's going in the opposite direction, okay? Hopefully that makes sense. Let's do one more question to verify that. So one more time, I'm doing the scale factor. And so I'm just going to pick a side. But before I do that, I want to check first to see if it's going to be an expansion or a contraction. So I'm starting out with this one, and I'm going to this one. So hopefully you can tell just by the picture that that's getting smaller. So I'm looking at a number between 0 and 1. So I'm looking at a fraction here for my scale factor, okay? Then I'm just going to pick one side. Let's just pick this side. I wouldn't pick the diagonals. The diagonals are too hard to tell. You can't really count a diagonal, so pick the straight sides. So let's do 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so that, remember, is the pre-image. That goes on the bottom. I like to always start with the pre-image so I don't forget what I'm doing. And then the corresponding side is this one right here. Okay, it's still the AD side, even though it's turned the other direction. And I get 1, 2, 3, 4, 5, I think. 1, 2, 3, 4. Oh, that last one is not 1. I'm sorry. It's hard to count them when they have those little tick marks. Now, I'm not counting these lines right here. I'm not counting these lines, guys. I'm counting the boxes, okay? So my students got confused with that, and I want to make sure you were not confused with that. So 1, 2, 3, 4. Okay. So 4 is the image after, and then if I reduce this, I can see that 4 goes into itself 1 time, and 4 goes into 8 2 times. So my scale factor is 1/2, but you have to be really careful because do you see how this is flipped the other direction? Kind of like I was talking about in the last problem. It's flipped the other direction, so it's going the opposite way, okay, of each other, which means this is going to be a negative scale factor. And so I'm just going to add a little negative sign here in front of my 1/2, and to make it -1/2. Now it's between, my scale factor is between 0 and 1, okay, when I take the absolute value, and therefore I know that this makes sense and this works. And what it's really saying is that this smaller image right here is half the size of this bigger one, okay? Half the size. And the negative tells me it's turned the other direction. All right, if you have questions about that, please contact your teacher. Okay, so I've kind of lumped 2.04 and 2.06 together because they are all about polygon similarity, okay? And there's a lot of information on this information to save page, so I suggest you take a snip and then you can go over it later. But we review a lot with proportions because similarity, proportions is huge in similarity. We use proportions to solve things all the time when we talk about similarity. So I'll remind you that a proportion is a fraction equal to a fraction, okay? So just like you see here, basically a ratio equal to a ratio, but we write ratios as fractions now. All right, we have this definition here that I wanted to remind you of because this is a question on your quiz. So we can think of this proportion now as being means and extremes. So B and C are called our means, okay? So these two parts of our proportion are our means. And those are, let me see if I can erase that and draw that better. Okay, these are our mean. And I know that those are our means. I'm just going to draw a line across. Okay, those are our means because those are the middles. So if you look up here, see how this is the middles? B and C, okay? So that's how I remember the means. The extremes are our outsides. So up here we have an A and a D on the outside. So those are the other direction, okay? Basically what it's saying is you can take AD and you can times those two and that will equal B times C. And so what we really call this is cross multiplying, and that's probably what you've heard it more or less being. The means extremes property here, product property, is really just cross multiplying, okay? And that's essentially what you needed to really understand with means and extremes. All right, so then moving on to similar. Similar right here is saying that figures are the same shape but not necessarily the same size. So an example would be over here. You can see with this problem, this is a bigger triangle. This is a littler triangle. So going off of the last lesson, we talked about expansion and dilation. So it's kind of like they're still similar if they're expanded or dilated, or expanded or contracted, meaning they're the same shape, but they're not necessarily the same size. Okay, the size has been changed. This symbol right here, the squiggly line, means similar to. So if you see that, know that that means similar. And then the postulate I wanted to focus on right here. Two polygons are similar if and only if there's a correspondence between their angles, so their angles match up, and their sides, so their sides are proportional, so that all corresponding angles are congruent. Okay, so that's key. For an object to be similar, or for two objects to be similar, their corresponding sides have to be, or corresponding angles have to be congruent, and their corresponding sides have to be proportional. Okay, and those are the two key things to make sure that a polygon is similar. All right, let's look at some problems here. So why are the rectangles similar? Show why or why not. So when we go ahead and look at this, we just need to set up a proportion. So when we set up a proportion, we need to go ahead and write it corresponding sides over each other. So I'm going to take this one because I can see that that's the vertical side there, so you could say, and I'm going to write it over this one, okay? 2.5 over 0.75, okay? And then I'm going to do the same thing with the other two sides, and I'm going to put an equal sign in between because remember, we're setting up proportions to see if these things are indeed similar. Okay, so now from here, to solve this, to determine if these are similar, we cross multiply. We use that products property, okay? And guess what? If we get the same answer out, the answer is yes, they're similar. If we get different answers out, guess what? They're not similar, okay? So we just go ahead and do that. 2.5 times 1.25 and 0.75 times 3.75. And I need to grab my calculator. Give me just a second. Okay, so hopefully you can still see that. I can't see my video while I'm doing this, so, and sorry about that, I wasn't prepared, I didn't have my calculator ready. Okay, so let's, 2.5 times 1.25, so I get 3.125, excuse me. And then I'm going to do the same thing with the 0.75 and the 3.75. So 0.75. And I get 2.8125. Okay, so you can see that these are not the same answer. 3.125 does not equal 2.8125. So these are not similar, okay? So these would be no, they're not similar. And the answer, the reason why we just showed it right here, we proved it when we cross-multiplied. All right, so now let's look at another question. Determine whether a pair of polygons are similar to each other. And I picked this one because I wanted to make sure that you were matching up corresponding sides. So you can see here that they've kind of turned these two figures and they're not facing the same direction, okay? And so if I was to turn this guy this way a little bit, then it would be facing the same way now. So just make sure you're matching up the angles, okay? So I can see that this has 3 congruency lines and this one also has 3. So those are the angles that are congruent, which means 5/15 would be the corresponding side, okay? And that equals the same thing as, and then you just pick one other one. You really only need 2 sides to determine it, okay? So I'm going to use 4 and 12. Hopefully that's okay with you. And then some of you are already looking at this and saying, yeah, Mrs. Guyman, those have to be similar because I can see that this reduces to 1/3. Oh, but guess what? This also reduces to 1/3. So that's another way to look at it. If you don't know how to reduce fractions and you just want to cross multiply, great, cross multiply. They're both going to equal the same thing, okay? But if you can see that they both reduce to the same thing, then that works as well, okay? You can also see that from 5 to 15, it's really getting 3 times bigger. From 4 to 12, it's really getting 3 times bigger. From 6 to 18, it's really getting 3 times bigger. Okay, so there's lots of ways to determine that. All right, the other thing that we did with 2.06 polygon similarity is finding missing angles and missing side lengths. So with this question right here, I'm telling you that they're similar, and now I need you to find the missing angles. Okay, so the key here is to match up the angles. If they're saying that triangle ABC is similar to EFG, then what happens is A and E are corresponding. That means they're equal, okay? It also means that B and F are equal, okay? And I'm matching these up for you so that we can see what's going to happen here on our triangles. And it also means that C and G are equal, okay? So here we go. We see that A is 64, okay? We see that G is 59. Well, guess what? If A is 64, E is also 64, right? And if G is 59, C is also 59. Okay? And so we now can find B and F because we know, first of all, that these are going to be congruent. So once we find one of them, we know the other. And second of all, we know that these 3 angles form a triangle. So I can do 180 minus 59 minus 64. Because those have to all add to give me 180. So if I know the 2 and I subtract them from 180, I can get the third. All right, so 180 minus 59 minus 64 gives me 57. And that, my friends, is our answer. 57 degrees is what B equals, as well as F, because they are corresponding. They're congruent. Okay, very last one, I promise, and I'm almost up on time here. These ones are similar now. I want to find the missing side length, which is this right here, okay? So now you can see that we're using sides instead of angles, okay? But you have to know that these angles are corresponding, right? To be able to determine that the sides are proportional. So I'm going to go ahead and write a proportion, but I think you're probably going to catch on sooner than I can get this proportion written. So if I see that this is 6/12, because those are corresponding, okay? That equals, and then you have to use the one that you're trying to find for it to work out, okay? So I'm going to do 10 over, and let's just call it x, okay? Now, to solve this proportion, we cross multiply. So we cross multiply 12 and 10 to get 120, and we cross multiply 6 and x to get 6x. And then, guys, I just solved. The last step is to divide by 6 so that we can find out what x is by itself. And so I divide here by 6. And so x equals, and I believe this is 20, right? And so that missing side is 20. And guess what? Some of you are like, I didn't even need to do that part because I could see that to get from 6 to 12, I really times it by 2, right? It's 2 times bigger. So to get from 10 to the answer, I have to times it by 2. And that's how we get 20, the second way or another way. Okay, if you have any questions, please bring them to your teacher's attention. And that's it for 2.01 through 2.06.